In this video, we're going to prove Bezout's lemma. If you like seeing proofs done all the time, lemmas, corollaries, then subscribe to my channel. Because that's basically all we do here. We prove theorems. If the theorem that you like to see proven, submit a request in the comment section, and if I know the proof, I'll get right on it. But for now, Bezout's lemma. It says that given a and b not both 0 in the integers, there exists another pair of integers, namely x and y, where the GCD of a and b, such that the GCD of a and b is a linear combination of a and b, ax plus by. The proof goes as follows. First thing you do is you define a set of all linear combinations of a and b, where these linear combinations are greater than 0, and u and v are both integers. U and v, they live in z. Okay. Now, I want to show that S is a non-empty set. Now keep in mind, S only contains positive integers. Well, since a and b are not both 0, assume that a is not 0. Well, a can be positive or negative then. Well, I want to show that something's in here, and that something must be positive. Well, the absolute value of a is positive, and this is equal to au plus b times 0. Now, if this is positive, and here it is, this will be an S, as long as u is an integer. This is equal to au, where u is equal to plus or minus 1, depending on the sign of u. Now, what on earth does this mean? Well, if a is less than 0, then the absolute value of a is a times negative 1 plus b times 0. If a is bigger than 0, then the absolute value of a is a times 1 plus b times 0. Either way, I wrote the absolute value of a as an integer multiple of a plus an integer multiple of b. And the value of what a is being multiplied by, which I called u, is plus or minus 1. So, clearly a is in S. So, Well, so the absolute value of a is in S, which implies S is non-empty. But S is a set of positive integers. So by the well-ordering principle, S contains a smallest element. Call this number D. And remember, since D is in S, D is a linear combination of A and B. Now, I make this big claim. I claim that D is equal to the GCD of A and B. Well, I need to show two things. I need to show that D is a common divisor of A and B, and then I need to show that it's the greatest one. Okay. Well, does D divide A? Okay. by their division algorithm, A is a multiple of D plus a remainder, where the remainder is in between R and D. It can equal 0, but it can't equal D. Let's assume that R is greater than 0. Either R equals 0 or R is greater than 0. Okay. So, based on this equation here, R is equal to A minus D cubed. But as I said a moment ago, since D is in S, D is a linear combination of A and B. But D has to be multiplied by Y. I meant to say by Q. A minus D cubed. Just like it says here. Now, working this out a little bit, it's A minus AQX minus, BYQ. Well, this is A times 1 minus QX plus B times negative YQ. Well, that puts, now since all of this equals R and R is positive, that puts R in S, because I did write R as a multiple of A plus a multiple of B. And since this multiple is positive, it's in S. Okay? But this implies that R is in S. But wait a minute. Wait one moment. And R is less than D. Okay? But this is a contradiction, because D was the smallest element in S. I claim I found another element in S that's smaller than D. That can't be. What can't be? Our assumption. So R is greater than 0 is not true. That implies only one other option. Remember, either R was either R was positive or R is 0. If R is not positive, then R is 0. Coming back to this equation, that implies that A is equal to D cubed. That implies D divides A. Similarly, D divides B. Okay. So D is a common divisor of A and B. This is good. Now I need to show it's the greatest one. So we pick another common divisor of A and B, and we show D is greater than it, or equal to. Okay, suppose C greater than 0 is another common divisor of A and B. Well, that implies that C divides a linear combination of A and B. Of course, I'm going to use this linear combination because that's the one that equals D. So C divides B. That means D is a multiple of C, where M, okay, so D is positive, and somewhere I wrote that C is positive. So if D is positive and C is positive, M has to be positive. Can't be 0, because 0 times the positive doesn't equal a positive. So M is either 0, negative, or positive. A negative times a positive isn't a positive. So it can't, m can be 0 or a negative. That means m is positive, where m is bigger than 0. But if m is bigger than 0 and m is an integer, that means m is at least 1. Now, if d is mc, I claim that mc is either less than or equal to c. Well, if m is 1, 1 times c equals c. If m is an integer bigger than 1, like 2, 2 times c is greater than c, I meant to write. 3 times c is bigger than c. 4 times c is bigger than c. And once again, if m is 1, 1 times c equals c. Well, this implies that d is at least c. So, d does equal the GCD of a and b. Let me just write that here, please. Oops. Not gonna let me just copy this, huh? Okay, so I'm just gonna move this down here. So D is equal to the GCD of A and B, but D is AX plus B, BY. So yeah, the GCD of A and B is a linear combination of A and B. And I proved just what I wanted to prove. Once again, if you like videos like this, subscribe to my channel. It's a no-brainer. If you like seeing proofs all the time, it's a no-brainer. Leave a comment. Most of all, see you guys in the next video, and watch and learn.